Okay, yeah, welcome to the second session of RTA 22, and thanks to the organizers once again for organizing this one. We have been missing this in the last year. We are delighted to have Debmalya Panigrahi for the second talk of today. Debmalya is an associate professor of computer science at Duke. After receiving his PhD from MIT, he worked as a postdoc for a while at Microsoft Research Cambridge before joining his current positions. Debmalya's main interests lies in a variety of algorithmic problems, mainly on graphs, and also in the area of so-called algorithms under uncertainty, which I guess encompasses mostly online algorithms. But as far as I am aware, he also dabbles a lot into related areas like algorithmic game theories, approximation algorithm, and so on and so forth. So honestly, I have been fascinated by his by his earlier papers on graph sparsification and so on and so forth. But more recently, he, along with some of his co-authors, they have some very exciting breakthroughs in the fundamental minimum cut problem in graphs. And not only is it a standalone result, but it has also opened up several new avenues to tackle problems in network flows, cuts, connectivities. And we hope to hear about some of these progresses from Debmalya over the two talks that he's going to give. So Debmalya, over to you.
Thank you, Shamantak. So as I was mentioning during the break, feel free to stop me if you have any questions. I'd be happy to take questions during the talk. Thanks to the organizers for inviting me. Thanks to Shamantak for this generous introduction. And thanks to everyone for showing up. I guess it's a slightly better time than it is out here, but still thanks for showing up. So I'm going to be talking about minimum cut algorithms, and I have roughly split my talk into two parts. The first part will focus on this new technique called isolating cuts and some of the ramifications of this technique. The second part will go into some other things. The two parts may not be completely balanced, so I might not finish the entire first part of the talk today, but we'll see how far I get. Okay, so this is based on joint work with a lot of people over several years and many papers. So I just wanted to mention everyone who has been involved in this process. So that's Amir Aboud from Weizmann, Roby Krautgamer, also from Weizmann, Ohad Trabelsi, who is a postdoc at Michigan, Ruoshu Chen, who is my student at Duke, Saura Chai, who is a PhD student at Aalto, Thachapal Sayanurak, who is at Michigan, Kent Kwanrad from Purdue, Danupan Nanongkai, who is currently at Copenhagen but is moving to MPI soon, and Jason Lee, last but not the least. I mean, he has been my closest collaborator in this line of work for several years now. So Jason is a postdoc at the Simons Institute, Berkeley. So let's start by defining a cut. This is something many of you already know, but a cut is simply a set of edges whose removal disconnects a graph. Okay, so it splits the graph into multiple components. And the minimum cut is a cut of minimum cardinality, so it's a minimum count of edges, or minimum weight if the edges have weight. And sometimes when we take the minimum, we focus only on cuts satisfying some particular conditions. So sometimes we would be talking of minimum cuts that are sort of unconditionally the minimum. Sometimes we would be talking about minimum cuts that are minimum among some subset of cuts. From the context, it would be clear which minimum cut we are talking about. In this talk, all graphs are going to be undirected, except on the last slide when I'm going to talk a little about directed graphs. The graphs can have parallel edges, so you can have multiple edges between the same pair of vertices. And the edges can have non-negative weights for the most part. Okay, so the first two types of graphs here are allowed. The first graph has non-negative weights. The second one has parallel edges, but the third one is not. So you cannot have directions on the edges as far as this talk is concerned. Okay, so the first type of minimum cut that we are going to be talking about is what's often called a global min cut. So this is simply a minimum cardinality or weight cut of the graph. So there's no conditions. Look at all the cuts of the graph, whichever has the fewest edges or has the minimum edge weight. That's what a global min cut is. We'll also be talking about ST min cuts, sometimes also called local min cuts. So this is again a minimum cardinality or weight cut, but with one condition. So there are two specific vertices, S and T, and these two vertices should be on different sides of the cut. Okay, and we know the famous max flow min cut theorem, which states that ST max flow is equal to ST min cut. If you haven't encountered max flows, that's fine. We are not going to be actually talking about any flows today, but I'll mention the word max flow, and whenever I do so, you should map it to ST min cuts. Okay, so an ST min cut can be obtained by running any max flow algorithm. This is a basic fact that we are going to be using throughout the talk. Okay, so here's an example of a graph. So in this graph, if I wanted to figure out what the ST1 min cut is, then as you can see, the smallest cut that separates S and T1, that has S and T1 on different sides, is the cut in the middle. So the cut containing that single edge of weight 1. That cut also happens to be the global min cut in this particular graph. But if you wanted the minimum cut that separates S and T2, so that's an ST2 min cut, then the global min cut has both S and T2 on the same side of the cut. So that's not a candidate anymore. So in this particular graph, the minimum ST2 cut is the cut containing the two edges incident on S. Okay, so that's a cut of weight 2, whereas the global min cut was a weight 1. All right, so these are the two, basically the two min cuts that we are going to be talking about today. And here's a very simple global min cut algorithm, maybe the first algorithm you would think about if I asked you to find an algorithm for global min cuts. So fix an arbitrary vertex in the graph, let's call that S. Now what you do is you find ST min cuts for all other vertices T. So you iterate over all the other vertices of the graph. There are n-1 vertices. So throughout I'll use n to denote the total number of vertices, m to denote the total number of edges. So if n is the total number of vertices, then there are n-1 vertices other than S. I iterate over all these vertices. For each such vertex, I denote it T. And then I find the ST min cut running max flow. And then eventually, after I'm done with all the n-1 iterations, I report the smallest of these ST min cuts as the global min cut. Why is this a correct algorithm? Well, the fact is that once I have fixed the vertex S, there must be at least one vertex that's on the other side of S, that's on a different side of S from in the global min cut. So there's at least one vertex that's separated from S in the global min cut. I don't know which vertex it is, but if I iterate over all the vertices, I'll hit that vertex at some point. And therefore, at that point, I'll get the global min cut as my ST min cut. Okay, so it's a correct algorithm. And therefore, the global min cut problem actually reduces to just n-1 max flow calls. So that's the baseline algorithm, but that's not where the state of the art is. So if you look at what has happened over the years, here's a very brief summary. There's a very large amount of literature on the problem. It's one of the basic questions in combinatorial optimization. But in short, the top box contains this naive algorithm of n-1 max flows. And I've actually quoted the running times for this algorithm, assuming you use the best max flow algorithms that we have available today. It's not very important to note what those times are. It's kind of complicated. We'll get back to those later. But there are better algorithms for global min cut, better than this naive algorithm. In particular, in the early 90s, there were a spate of algorithms, all of which got the same running time. The running time was m times n. And I'll use this O tilde notation to hide subpolynomial factors, so things like polylogs and so on. There are many polylogs in all these runtimes. We are not going to be talking about those. So you can get a running time of m times n deterministically using any one of these algorithms that came in the early 90s. And then there were a series of randomized algorithms. So the first one perhaps is the Karger-Stein algorithm, also called the recursive contraction algorithm. So this obtained a running time of n squared. So remember, for a connected graph, n squared is better than m times n. And then that was further improved to a running time that's nearly linear. So it's almost m by Karger in 1996. And this is really the best you can do modulo those polylog factors that I'm hiding. Because even to read the input, for if you wanted to read in a graph, you would spend at least m time because there are m edges. So you have to read in, for example, m weights. Now, one interesting thing to note is that if you compare the running time with a single max flow call, then the deterministic runtime for global connectivity, for global WinCut, is actually slower than max flows. So we can deterministically find max flows much faster than m times n. On the other hand, the randomized algorithm is a linear time algorithm, so that's much faster than max flows. We still kind of don't know how to do max flows in linear time. Okay, although I'll qualify that statement a little later. Okay, so that's the state of the art, and it has this like strange situation where if you were willing to use randomization, then you can then the global WinCut problem seems to be easier than ST WinCut. If you wanted to be deterministic, then the global WinCut problem seems to be slower, seems to be more difficult than ST WinCut. So when we set out in this project, maybe the first question that intrigued us was the following. So we were just wanting to find a deterministic global WinCut algorithm that could match a deterministic max flow algorithm. Okay, because as I said, there was this strange inconsistency that if you wanted deterministic algorithms, global WinCuts had slower runtimes than max flow. Again, this question, at least one form of this question, was asked originally by Karger in the mid-90s. There was no progress on this for almost 20 years until this beautiful paper of Kawarabayashi and Tharup about 6-7 years back. So they showed that, in fact, you can solve global WinCut deterministically in near linear time, in O tilde m time, which is the same as what you can do randomized, but with the crucial restriction that this algorithm only works for simple graphs. Okay, and this restriction is kind of pretty, this is a significant restriction in the sense that it's not just that the algorithm is slow if your graph is non-simple, but the algorithm is actually wrong. So it doesn't give you the correct answer if the graph is non-simple. And I should mention that this paper actually won the Fulkerson Prize last year. Okay, so we had this for simple graphs, but we didn't know what we could do if there were parallel edges. We certainly didn't know what we could do if edges had weights. There was an improvement by Monica Hensinger, Satish Rao, and T. Wang. But the improvement is only in the polylog factors. So the original result had something like log to the 12. I think after the improvement, it went down to log squared. And the improvement was also important in terms of providing a new combinatorial perspective to the algorithm. But fundamentally, it didn't change the state of the art in the sense that we still didn't know what to do if we wanted to go beyond simple graphs. So our main theorem, the first one in this line of work, this was work with Jason Lee, was that there is a deterministic algorithm for the global WinCut problem that runs in time that's equal to polylog max flow calls. Okay, so this is not quite as good as you might hope. So this is not quite getting it down to near linear time, which you can do if you were allowed randomization. but this is getting close. It's at least getting it down to max flow. Okay, and in fact, Jason didn't quite stop there. So in a follow-up work next year, he actually showed that you can go all the way down to near linear deterministically. So I won't actually talk about the second result because that will be a detour. It uses a set of techniques that are different from what I want to talk about. But I'm going to talk about my result with Jason because that will introduce this very nice idea of isolating cuts that we are going to see quite a lot of. All right, so as our main new idea in this result is isolating cuts. So what are these? So let's go back to the simple min-cut algorithm that we started with. So recall this algorithm. What did it do? You fixed an arbitrary vertex as S. Then you found ST min-cuts for all the other vertices designated as T. And then you reported the smallest of these ST min-cuts as your global min-cut. Now let's do a thought experiment. So suppose after you had fixed this vertex S, someone came and gave you some vertex T that's on the opposite side of S in the min-cut. Okay, so this is some oracle that gives you a vertex T. Now, if you got hold of such a vertex, the vertex T that's on a different side from S in the min-cut, then all you would do is you would just find the ST min-cut for this one vertex T, and you would report it as the global min-cut, right? So in some sense, the previous simple algorithm, what it's doing is it's kind of blindly searching for a vertex T that's on a different side from S. Okay, and that kind of raises this natural question, is there a way to efficiently do the searching? Can we find vertices S and T that are on different sides of the global min-cut in some efficient manner? If we are able to do that, then once I have these two vertices, I can just run max flow and I will be done. Okay. So now let's look at this question in two different cases. The first situation is if when the min-cut is balanced. By balanced, I mean that you have n over 2 vertices on each side of the cut. So that's perfect balance. Don't quite need perfect balance for a statement of this sort, but let's go with that. So if your min-cut is perfectly balanced, you have exactly n over 2 vertices on both sides. Then finding a pair of vertices S and T that straddle the min-cut, that are on different sides of the min-cut, is kind of simple. So all you need to do is just sample two vertices uniformly at random. And with about probability half, you will have these two vertices on different sides of the min-cut. Right, so with a probability about a half, both of the vertices would be on the same side. With probability about a half, they would be on different sides because your two sides are balanced. Okay, so with probability half, you have a good pair of vertices on which you can run max flow to find your min-cut. And if you wanted to boost this probability further beyond half, all you do is just repeat this process a bunch of times. Okay, so you sample log n times instead of just once. So then the above property holds with high probability. So there's at least one pair ST that's straddling the min-cut. And then you just return the smallest ST min-cut across all these log n runs. Okay, so if the min-cut is balanced, then in fact you have a very simple algorithm. Of course, I'm using randomization here, and my whole purpose was not to use randomization. So we'll go back and fix that later. But for now, let's allow randomization. Let's try to develop our ideas a little better. So if the min-cut is balanced, we have a simple solution. The problem is if the min-cut is not balanced. So let's say the min-cut has only k vertices on the smaller side, and think of k as being small. Then one thing I could do is I could sample vertices at rate about 1 over k. So I just take each vertex independently, sample it with probability 1 over k. If I do that, then with constant probability, I'll have exactly one vertex on the small side in the sample. Right? Because I'm sampling k vertices, what's the chance I'll sample exactly one of them? If I'm sampling at rate 1 over k, that's a constant. Right? Because I expect to see one vertex, and I'll have a constant probability of seeing exactly one. Now I can repeat this process log n times. I can sample log n times. And again, this property that you see exactly one vertex on the smaller side in one of the samples, this property now holds with high probability. Okay, but this should raise sort of two red flags. The first one is we don't quite know K. So remember, K is the number of vertices on the smaller side of a min cut. So we don't quite know K, so we don't know what rate to sample at. But this turns out to be a fairly trivial problem, minor problem that we can handle. We'll see how to handle it later. The much bigger problem is, let's say K equals 1. So I have exactly one vertex on the smaller side. Then what I'm saying above is that I sample at rate 1. So with probability 1, I'm sampling vertices. What does that mean? I'm basically taking all my vertices. So really, I have hit the smaller side at exactly one vertex, but I haven't really reduced the number of vertices in the graph. So if I haven't reduced the number of vertices, how am I hoping to get any benefit out of that process? Okay, so remember in the previous algorithm, we were sampling two vertices, S and T, in the balanced case. So the fact that we had just two vertices allowed us to run max flow. If you have a bunch of vertices in my sample, how do I run max flow, right? And of course, if I have n vertices, which would be the case if K equals 1, then I certainly can't run max flow for all pairs. That's way too expensive.
Debmalya, so I'm just trying to understand. So for K equals to 1, the problem is anyway easy, right? You can just check the degree. Okay, okay. Yeah.
That's right. Yeah. So this is just for
illustration.
Yeah, for illustration of the fact that by itself, the previous property is not useful. As Shamantak says, if you knew K equals 1, you could just check degrees. But instead of K equals 1, think of K equals 100, for instance, let's say. Okay.
Hey, but like when K is rather a quick question, but K is small, like other arbitrary, like instead of picking a pair, you could have fixed an S and then tried to find a T.
Right. So finding the T is where the problem lies. So let's say K equals 100. Right. So if you actually wanted to find a T in that set of 100 vertices, you end up sampling at least like something like an over 100 vertices. Right. So you have just reduced from sampling n vertices to sampling n over 100 vertices. That's not going to give you any improvement.
I guess what I'm trying to get at is like if it's imbalanced, then like picking an S with like say some constant probability tells me that it's on the larger size.
That's right.
But then I can say probably just find min cuts to all other vertices from S. But you're probably saying that that's a expensive process.
Well, that was the original simple algorithm, right? That's going to take n-1 flows.
Okay.
Does that make sense?
It does. It does. Yeah. Thanks.
Yeah. Any other questions before I keep going? Okay. Right. So let's keep going. So let's look a little deeper into what's really going on. So let me denote the smaller side of the min cut by S. And as we saw in the previous slide, if we are able to sample at rate 1 over K, where K is the size of S, then let's say we can obtain a sample of vertices that we call T that has this property that there's exactly one vertex in which it intersects with the smaller side. Okay, so this is something we can obtain. The thing that we can't control is the size of T. So as this previous discussion told us, T can be as large as n over 100, for instance. Okay, so let us define a new problem. So let's suppose we are given a graph and a subset of vertices T. Now, we define a problem which asks us to find a set of cuts, not just one cut. It asks us to find the following cuts. For every vertex in T, I want a minimum cut that separates this vertex little t from the rest of the vertices in capital T. Okay, so one way of thinking of this is that you fix this vertex little t, contract all the vertices other than little t into a single super vertex, let's call that S, and now find the ST min cut. Okay, and I want you to do this for every single vertex t in the sample capital T. Okay, so if you could solve this problem, then you would be done, right? Because you know that at least one of these vertices in capital T is the unique vertex on the smaller side of the min cut. I don't know which that vertex it is, but there is one. So at some point, I will hit that vertex as little t. Okay. All the other vertices in capital T are on the larger side of the min cut. So now if I ask for the minimum cut that separates little t from every other vertex in capital T, then that minimum cut will be the global min cut. Okay, simply because the global min cut has exactly this one vertex little t on the smaller side in the set capital T. Okay, so this is what we call the isolating cuts problem.
Debmalya, could you repeat this? I couldn't follow very properly. So could you repeat this?
Okay. Okay. So suppose I give you a graph and a subset of vertices in that graph. And I also tell you that there's some vertex hiding in this subset. That's a unique vertex on the smaller side of the min cut. Okay. So every other vertex in capital T is on the larger side. There's one unique vertex in capital T that's on the smaller side. You don't know which vertex it is, but there is such a vertex in capital T. Okay. So now if that vertex, if I call it little t, then the minimum cut that separates little t from all the other vertices in capital T is in fact the global min cut as well.
Correct.
Okay. So now if I can find all the minimum cuts that separate all the candidates little t from the rest of the vertices in capital T, then among them, whichever is the smallest will be my global min cut.
Okay.
Does that make sense?
Yes, thanks.
Right. Any other questions? Okay, so that's what we are going to call the isolating cuts problem. Okay, so I'll give you a graph, I'll give you a subset of vertices. Can you find me the isolating cuts? Where what are the isolating cuts? These are the cuts that isolate a single vertex in this subset from the rest of the vertices in the subset. Okay, it's the minimum cut that isolates a single vertex in the subset. So again, important thing to note, it's not one cut. So when I give you the set T, the number of cuts I'm asking for is the size of T. For every vertex in capital T, I'm asking for a minimum cut. Okay. So how do I solve isolating cuts? So of course, the naive algorithm would be to iterate over all possible values of little t. So I take every possible vertex in capital T, contract the rest of the vertices into a super vertex, find the ST min cut. The problem, of course, is that this takes something like T max flow calls. Actually, it shouldn't be T minus 1. It's actually T max flow calls. But T itself, the size of this subset that I give you can be as large as n. I haven't actually I haven't given you any guarantees that the size of T is small. Okay. So, and in particular, in that case that we saw earlier where k equals 1, the size of the sample will in fact be n. Okay. So this naive algorithm is no good because this is really taking us back to this algorithm that's running in max flows. Our main contribution in this paper is what we call the isolating cuts lemma. So we show that the isolating cuts problem can be solved in log T max flow calls rather than T. And this is interesting in the sense that the number of cuts that I am retrieving from this algorithm is actually a lot more than the running time of the algorithm. Remember that the number of cuts that I am retrieving is like T. On the other hand, the number of max flow calls that I am making is only log T. Right? So which is kind of seems a little strange, right? Because that says that somehow I'm managing to retrieve a lot of cuts from a single max flow call. right? And we'll see how that happens. Okay, any questions about the statement? The next few slides will aim to prove this statement, at least to some extent. But
could you repeat the last statement?
Could I repeat what? Sorry.
The last statement.
Yeah. So the isolating cuts lemma says that this isolating cuts problem. So the isolating cuts problem is the stuff in black on top. This can be solved using log t max flow calls rather than t max flow calls, which would be the naive way to solve it. Okay.
Hey, Debmalya?
Yeah.
So do you really need the size of key min cuts, or do you just want the min over all such cuts?
I just need the min over all such cuts, but I don't know of a way to do that better than actually finding all of them.
Yeah, okay, thanks.
Okay, all right. So let's delve into isolating cuts a little more. Okay, so here's, I'll actually give an algorithm for this. So for the isolating cuts problem. So let's say I have this graph that I have shown here, and the vertices I have circled in green are the vertices in T. Okay, so the vertices T0, T1, T2, and T3 are the vertices in capital T. Now, the first thing I do is I encode these vertices in binary. Okay, this encoding is not so important how precisely it's done, but for the sake of concreteness, let me encode it as 0, 0, 0, 1, 1, 0, and 1, 1. Okay. Now, what I do is I look at every individual bit position. So let's say I'm looking at the first bit position, the most significant bit, and I partition the vertices in T into those that got an encoding of 0 and those that got an encoding of 1. Okay, in this particular example, if I'm doing the partitioning based on the first bit position, then A and C are on one side of that partition, B and D are on the other side of the partition. Now what I do is I contract all the vertices that got a bit position, a bit value of 0, contract all the vertices that got a bit value of 1. Okay, so this creates a pair of super vertices, and I just find the ST min cut for this pair of super vertices. Okay, so for bit position 1, I'll find the minimum cut that separates AC on one side and BD on the other side. The minimum cut in the graph that under this constraint, under the constraint that AC is on one side and BD is on the other side. And I'll do this for every bit position. So when I get to the second bit position, now AB is on one side and CD is on the other side. Okay, so I find these, I run these max flows and I find ST min cuts for each bit position. Okay, so of course these are log T, the number of like I'm encoding T bits. T vertices. So the number of bit positions is log T or O of log T. And therefore, these max flow calls are returning O of log T cuts. But the important thing to note is that every pair of vertices in T, these got different bit encodings, right? If I take any pair of vertices, they have different bit encodings. What that means is that at least one of these log T bit positions, the encoding differs, right? So one vertex got a 0, the other vertex got a 1, at least at one bit position. Okay, so every pair of vertices in T is separated by at least one of these log T cuts. So what this means is that if I take all these log T cuts and remove all those edges from my graph, then in fact I will split the graph up into at least T pieces. And in each of these T pieces, I'll see exactly one vertex from capital T. Right? So again, why is that the case? For any pair of vertices, they differ in some bit position. So when I remove the min cut for that particular bit position, that pair of vertices will get separated. They are no longer connected. Right? And this will happen for every pair, which means that when I remove all these log T cuts from my graph, I'll split the graph up into pieces, at least t pieces, and I'll see only one vertex from t in each of these pieces. Okay, so that's the basic observation that's going to be important. So now what I do is I take these pieces individually. So in this particular picture, I call these pieces S0, S1, S2, and S3. So as you can see, T0, T1, T2, and T3 have gotten split into these 4 pieces. Now I take each of these pieces individually. For instance, let me illustrate it through S3. So I take S3. I take all the other pieces, S0, S1, and S2 in this case, contract everything else into a single supervertex. Okay, so this is phase 2 of the algorithm going on. Phase 1 was this bit position based partitioning. Phase 2, I take each of these individual SIs, contract everything else into a single vertex. Let me call that as ZI. Okay, so in this particular example that I have shown here, I have S3, which is uncontracted. Everything else, S1, S2, and S0, I contract into Z3. Okay, and then now note
do
that yeah.
Sorry, do S3 will contain more than one terminal, one vertex from T?
Yeah, it cannot contain more than one. None of these pieces can contain more than one. So as we were just saying, if you have take any 2 vertices from T, one of the bit positions in one of the bit positions they differ. So that particular min cut will separate the pair.
Okay, thanks.
Okay. So S3 contains some unique terminal. Let's call that T3, some unique vertex from T. Now what I do is I find a minimum cut from T3, between T3 and this contracted vertex Z3. Okay. So for a second, let's step back. What were we really intending to find? We were intending to find the minimum cut between T3 and the terminals T0, T1, and T2 contracted. Okay. Now, in general, in this particular example, S0, S1, and S2 are exactly the terminals, but in general, they can contain other vertices. So what I'm ending up finding is not T3 contracted and T0, T1, and T2 contracted on the other side. But what I'm ending up finding is the minimum cut with T3 on one side and all of S0, S1, and S2 contracted on the other side. Okay, so a priori, it's not clear that I'm finding the right set of cuts. Okay, but at least there's some semblance of going in the right direction, right? Because I was interested in finding these cuts that separate Ti and all the other terminals. Instead, I'm finding these cuts that are separated by Ti and all the other terminals, but plus other things. Okay. Was there another question? No. Okay.
So far you were like invoking max flow only on the original graph, but now you are invoking it on this induced graph GI.
That's right. That's
and
right.
the hope is that in an amortized sense, the size of GI would be small.
Perfect. Yeah, we are getting there.
Okay.
I have a question. So these S0, S1, S2 contains vertices apart from the terminals as well, right? So
they can, yes.
Okay.
Yes. In general, they can. In this particular example, it doesn't, but in general, they can. Yes.
Okay. Thank you.
Any other questions? Okay. So this is really the picture I have. So I have this sort of giant vertex Zi containing everything else, all the other Sj's, and I have this uncontracted part Si containing this terminal Ti, containing this vertex Ti from T. Okay, so the first claim is that in fact the Ti Zi min cut in this graph Gi, which is this contracted graph, is in fact a min cut, also a min cut between Ti and the other terminals. Okay, so this is not obvious, but the proof is not so difficult. It's by some standard property of min cuts called uncrossing. That's something I'm not going to talk about. Like, I'm not going to describe this property here, because it will be a bit of a detour. But this is uses fairly standard techniques. Nothing special going on here. Okay, so I am finding the right cuts. Now, how many max flow calls is my algorithm making? So there were two phases, remember. The first phase was this phase that used these bit positions. So there clearly we are running log t max flow calls because there were only log t by bit positions. So that's great. Problem is the second phase. The second phase is actually using t max flow calls because there are t different SIs, and for each of them I'm running max flow. But now if you look at the actual graph on which I'm running max flow, then you notice that there are two types of edges. There are edges that are inside any of these sets SI. So these edges only appear in one of the calls, right? Whichever, if an edge is inside a segment SI, then it only appears in the ith call. It doesn't appear in any other call. But there are also edges that cross between segments. So let's say there's an edge between SI and SJ. Now that edge can appear in at most two calls. So it can appear in the call for SI, the max flow call for SI. It can also appear in the max flow call for SJ, but not more than that, only two. So that says that cumulatively across all these T max flow calls, we are operating only on 2M edges or O of M edges. Okay, so that's where this inconsistency is being resolved. So remember I told you that we are finding T cuts, but we seem to be only using log T max flows to find these T cuts. So really what's going on under the hood is that we are running T max flows. It's not log T max flows, but the way we have set it up, we are ensuring that cumulatively these T max flows are only operating on 2 times M edges. So really the dominant term is the first round that's actually running log T max flows on the original graph. The second round, which is actually running T max flows, is only costs us equal to 2 max flows, something like that. Okay. So overall, when you put this together, then you have the isolating cuts lemma. So now we have found all the isolating cuts, and we have only used up log T max flow calls. Okay, so I'll pause for a second and take any questions. So we will now get into how to use the isolating cuts lemma. So firstly, if you missed something in the proof, you can rejoin now because we are not going to use that proof anymore. But if you had any questions about the proof, I can also answer them before we move on. Okay, so if there are no questions, let's now try to use this lemma. Okay, and let me start off by using it to define a simple randomized algorithm for min-cut. So as we said earlier, randomized algorithms are not going to improve the state of the art. We already have near linear time algorithms, but this will illustrate how the isolating cuts lemma can be used, and this will be useful later as well. So here's a very simple randomized algorithm. So what I do is I first try to guess the size of the smaller side of the min-cut. Okay, so remember we had that red flag earlier that we didn't know how large the smaller side is, so we didn't know what rate to sample at. But let's just try to guess this. So we try all possible values of the smaller side. I just scale everything by factors of 2 so that we don't have too many rounds of guessing. Okay, so I guess the value of I from 1 through log n, and the size of the smaller side is 2 to the I. Okay, for one of these i's up to a factor of 2. Then once I've fixed a value of I repeat the whole process log n times. This is just to boost the probability of success. Remember, we had this thing where the probability of success was only a constant. We need to boost this up to high probability. So we just repeat it log n times. But now I have fixed I, and we are in a particular iteration. Now what I do is I simply sample vertices at rate 1 over 2 to the I. I form a subset T and run isolating cuts. Okay, so now I have these log squared n rounds of isolating cuts. They return a bunch of cuts to me. Whichever is the smallest cut that I see, that's the one I output as my global min cut. Okay, that's as simple as the algorithm is. Why is it correct? Well, with high probability, there's an iteration where the smaller side of the min cut has exactly one vertex in T. This is an argument we have gone over earlier. The fact that we are sort of that our guess is missing the right value by a factor of 2 doesn't really make any difference. That just changes the constant. So there's an iteration where we are actually hitting the smaller side at one vertex. And in that iteration, the isolating cuts lemma will return the min cut. Okay. Now, of course, every cut that I return in the entire algorithm is a real cut of the graph. So at the end, if I'm returning the minimum among all the cuts I saw in isolating cuts, then that must be the global min cut as long as isolating cuts at some point gave me the global min cut. Okay. So that just establishes that the algorithm is correct. And of course, the running time is dominated by these calls to the isolating cuts lemma. So that's just polylog and max flows. There's really nothing else going on in the algorithm. Everything else is very efficient. It's just sampling. Okay, so that's a very simple randomized algorithm. But how do we de-randomize this? So if you go back to the randomized algorithm, the isolating cuts lemma itself was running a deterministic algorithm, right? So we discussed this algorithm, there was no randomization in it. The only randomization is in the sampling, in trying to obtain the set of vertices that hits the smaller side at a single vertex. Okay, so we need to de-randomize that. So let's call a set of vertices with this property that it hits the smaller side of my min cut at a single vertex. Let's call that an isolator. Okay, and our goal then is to find an isolator deterministically. If you're able to do that, then we can use the isolating cuts lemma. We would be done.
Hey, can I ask a quick question before you move on?
Yeah, absolutely.
So in the previous slide, it's sort of stark that different T's, so let's say capital T and capital T prime, they don't help each other in the sense that if they're disjoint, then or let's say supersets of each other, like one solution for one does not help. Like, so you have to really do it for scratch for all T, or am I, like, maybe there's a smarter encoding that lets you.
It could be, but it would only save on logs, so we didn't really think about it.
Okay.
I mean, in any case, the total number of T's you're working with is like log squared.
Okay.
Okay. So, so our goal is to find an isolator deterministically. Was there another question?
Yeah, Debmalya, so I want to ask, do you want the size of the isolator to be the size of the smallest set of vertices, or does that not matter?
No, the size of the isolator will actually be roughly equal to 1 over T2 to the I times N.
Okay.
Right, where like you are at level I, and I have no idea what the smaller side looks like.
Right. Okay.
Okay. So how do I find an isolator deterministically? That's our new question. So first, let's extend the idea of isolators a little. And let's call a set of vertices an almost isolator if instead of hitting the smaller side at one vertex, it hits the smaller side at most a polylog n vertices. So this is saying that, well, I don't have too many vertices from the smaller side, but it's not, maybe not precisely one. It might be a little larger. It might be polylog n. Okay. And the translation from an almost isolator to an isolator is given by this claim. So we show that if you are given an almost isolator, then deterministically you can find a small list of subsets of this almost isolator such that one of these subsets is indeed an isolator, an actual isolator. Okay, and this uses something called color coding, which was introduced by Alon Euster and Zwick in a very different context. I won't go into this because roughly speaking, but as an exercise, what you can think about is the following. Roughly speaking, if if I gave you an almost isolator, there is a very simple way of getting an isolator by just sampling the almost isolator. Okay, so and I'll if you are interested, I'll let you figure out how to do that sampling. But it's a very simple sampling technique. Really, what this color coding does is it de-randomizes sampling. Okay, so this is just a clever way of doing the sampling deterministically. But from now on, I'm going to assume that as long as once I have an almost isolator, once I have polylog n vertices on the smaller side, I'm done. I can rely on this claim from that point onward. Okay, so what's our how far have we progressed so far? So we have said that given a subset of vertices that whose intersection with the smaller side of the min cut is polylog n, given such a subset, we can find the min cut in polylog n max flow calls. Okay, so it's really a question of how to find such an almost isolator. So the technique that we use to find an almost isolator, we call that deterministic sparsification. Doesn't really have anything to do with like cut sparsification, which is a common topic in graph algorithms, but we couldn't find a better name, so we just called it deterministic sparsification. So what does this really do? So it says that suppose I give you some set of vertices T that's not an almost isolator. What does that mean? That means that T has more than polylog n vertices on the smaller side of the min cut. Okay, but importantly, assume that T actually does straddle the two sides of the min cut. So it's not all on the larger side. There are vertices from the smaller side, there are just too many. So if that happens, then the deterministic sparsification algorithm that we design, it computes a set of vertices T prime that has two properties. First, T prime reduces the size of T by a factor of 2. So T prime is no larger than half times T. And second, T prime continues to have vertices from both sides of the min cut. Okay, so you still have vertices from both sides. The size of the set drops by a factor of 2. Now note that it doesn't explicitly say anything about how many vertices it has from the smaller side. It's not that T prime is better in terms of directly getting you closer to an almost isolator. It's possible that T prime has just as many vertices on the smaller side as T did. Okay, so that's not our measure of progress, but T prime overall is becoming smaller. So if I have a deterministic sparsification algorithm, an efficient one, then here's our overall algorithm. So first we initialize T to be all the vertices V. Okay, so clearly at this point T does straddle both sides of the min cut trivially. Now we repeat multiple times, and we repeat until the size of T becomes really small, becomes less than polylog n. In each step, I don't quite know if T is an almost isolator or not. Okay, so let me assume that it's an almost isolator. And let me use color coding and the isolation cut lemma to obtain minimum cut candidates. This is assuming that it's an almost isolator. Of course, if it's not an almost isolator, I'm just getting junk cuts. Okay, so the first step is assuming that it's an almost isolator. Second step says, let me also assume that it's not an almost isolator, because I don't know what it is, like whether it is or not. So if it's not an almost isolator, then I have deterministic sparsification. So I also take T and I apply deterministic sparsification, and that halves the size of T. Okay, so what's really going on? I started off with all vertices. I don't know if that's an almost isolator. At that point, I assumed it is, ran my color coding and isolation cut lemma. I also assumed it's not, and I halved the size, and I repeated. Right, so at some point, either T becomes an almost isolator, because right, or it continues to be not an almost isolator and therefore have more than polylog n vertices on the smaller side. So of course, if it became an almost isolator at some point, then that particular iteration, step 1 will actually find min cut. If it did not become an almost isolator at any point, now note that T has dropped to less than polylog n vertices at the end of this loop, right? So at this point, if it never became an almost isolator, then it must be that T is still straddling both sides of the min cut by the deterministic sparsification property. It's straddling both sides and it has only polylog n vertices. So at this point, by definition, it must be an almost isolator. Okay, so what we have established is that either T is an almost isolator in one of these loop iterations, or it's an almost isolator once I exit the loop. Okay, so now what I do is after I exit the loop, I take all pairs of vertices in T. So there are only polylog n pairs, and I find max flow and add the ST min cut to my candidate. So if T is an almost isolator at the end, if it's still straddling the two sides of the min cut, then this last step will catch the min cut. Okay, so now I have created this enormous list of candidates. Well, I'm saying enormous, but polylog n list of candidates across all these steps. I look at all these cuts, and whichever is the smallest, I return that. Okay, so that's my entire algorithm. So as long as I have deterministic sparsification, I am done. I have an algorithm that finds my min cut deterministically. All right, so I think I have a few minutes left. So I'll just finish deterministic sparsification and we'll take the rest of it tomorrow. Okay, so the missing piece is deterministic sparsification. And as I said, the goal is that if T is intersecting the smaller side at more than polylog n vertices, then I want to halve the size of T, and I want to make sure that I'm still straddling both sides of my min cut. Now, intuitively, what we do is the following. So we want to find a vertex partitioning of the entire graph that has two properties. The first property is that it should have a small number of components in the partition. So I don't want to partition it into singleton vertices. Should be a small number of components. And I want to also ensure that the min cut does not cut into any one of these components. Okay, so let's say the min cut actually keeps all the components intact. The entire component goes to one of the two sides. If I suppose I had these two properties, then all I need to do to obtain T prime is just select one vertex in T from each of the components, right? Because the number of components is small, so that ensures T prime is small. Since the min cut doesn't cut through any of the components, by choosing just one vertex from each component, I ensure that my new set actually straddles the min cut as well. Okay, because all the vertices in a single component are on the same side of the cut. So by choosing any one and discarding the rest, I am not going to miss out on hitting any one side of the min cut. So if I had this kind of a vertex partitioning, then I'm golden. I can just choose one vertex from each of these components and I would be done. So how do I ensure these two properties? Remember, the two properties are small number of components, and the second is that I want my min cut not to be cutting into any of the components. So for small number of components, precisely what we want is the total weight of crossing edges. So the edges that go between the components, we want this total weight to be lambda, which is the size of the min cut, times the number of components T, times some parameter phi. Think of phi to be about 1 over polylog n. Okay, and if that is the case, then it's not hard to show that the number of components will be like phi times the size of T. Okay, so roughly speaking, now you can see the number of components is about T times 1 over polylog n times some polylog coming from the O tilde. So if I can adjust these terms, adjust the value of phi correctly, then I'll get like T over 2 components, or maybe T over 4 components. Now the other property was that the min cut does not cut into any component. For that, what we want is that every component expands. So if you are familiar with expanders, expanders are these graphs which where sort of if you run a BFS, then the BFS is very broad. Okay, it's a sort of a fat wide tree. So if you have an expander, then the min cut can't really cut into an expander too much, because if it cuts into an expander, then it will consume a lot of edges, right? So the min cut will not remain a won't remain a small cut, right? So we want each component to be expanding, and we want the number of edges connecting the components to be small. Okay, and that there is a perfect tool for this that's called expander decompositions. So in particular, we use a deterministic expander decomposition, originally due to Chujoy et al., but the particular version that's most useful for us is due to Lia and Saranura. Okay, so eventually what we have after,
So this is linear time, right?
This is near linear. So, right, so the Chujoy result is like m to the 1 plus epsilon time, where the epsilon goes into the value of phi. But the next one, Lee Saranurak, is actually near linear time. So that's like m times polylog. Yeah. Okay, so now I have my expanded decomposition, and really I have sort of three cases. I have trivial components where the component doesn't even intersect my set T. I have small components where the intersection is small. It's kind of like less than 1 over phi squared. And I have large components where the intersection is large. Okay. So now how do I select T prime? Trivial components I just ignored. It doesn't even have any vertex from T, so I don't care. The small components, I select any one vertex. Okay, the point is that there are very few vertices from T in these components. So even if I choose one vertex, I'm going to be so the min cut cannot actually cut in and isolate that vertex. The large components have a lot of vertices. I need to be a little more careful here. So here I choose about 1 over phi vertices. Okay, but remember the large components, each of them consumes 1 over phi squared vertices from T. So overall, the total number of vertices I end up choosing is something like phi times T. Okay, and this is exactly what was at most T over 2. Okay, so this slide, I'm sort of suppressing a lot of details. So if this seemed to sort of too hand wavy, that's fine. I am suppressing details here. But the bottom line is that if you now go back to this algorithm that we described earlier, so then that establishes our theorem. So the theorem, as I said, is that there's a deterministic algorithm for the global min cut problem that runs in time equal to polylog max flow calls. Okay, so I think I'll pause there. So because I've basically run out of time, and we'll start here tomorrow. And I'm happy to take any questions at this point.
So hi Debmalya, will you tell us more details about this deterministic sparsification, or we should read somewhere else?
No, so I'm not going to. So this, I would, I welcome you to read the paper for this.
Okay.
I'm not going into it because in some sense, there's not a whole lot of novelty here. What's going on here is that we are just doing, it's a sort of case analysis of all these different cases just to show that you make sure that you straddle both sides.
But will you at least tell us about what this expanded, what is that called, decomposition is?
So the expanded decomposition
may not even know what this expanded decomposition.
Right. So this expanded decomposition is exactly obtaining the properties that I have written on this slide. So you, given any graph, you can partition it into components where each component has an expansion of phi. Phi is a parameter you can control. Mm-hmm. And the total number of edges between the components is like phi lambda times the total number of components.
Okay.
So it's exactly what's written here. How you obtain this in near linear time is complicated, and that's not even in our paper. We are just using a theorem from somewhere else.
Sure. Okay. Thanks.
I mean, one sort of structural way of thinking of this is that any graph looks like, at the right level of granularity, looks like a bunch of expanders, So a bunch of, let's say, random graphs, but which are connected by things that look very non-random, but the connections are few. So it's a very sparse connections. What's dense is inside these sets, but that dense part is very much like a random graph.
Okay. Okay. Thanks.
Other questions?
Yeah. Yeah. Okay. First of all, let me thank you on behalf of everybody, because I guess you cannot hear the claps. But yeah, more questions, if any. Okay. So if there are none, then I guess we close this session. And thanks, Debmalya, once again. We look forward to your second talk tomorrow.